Good day, and welcome to our comprehensive exploration of the features of three major operating systems: Windows, Linux, and Mac OS. Today, we'll be diving deep into various aspects of this operating system. Before we embark on our journey through the world of Windows, Linux, and Mac OS, let's first understand what an operating system is. An operating system, OS, is a fundamental software component that manages computer hardware and provides services for computer programs. It acts as an intermediary between the hardware and software, enabling users to interact with the computer system effectively. Windows is developed by Microsoft and widely used in business and consumer space. Linux is an open source operating system and used for heavily in business infrastructure and servers. And last not the least, Mac OS is developed by Apple and mainly used in the consumer space. Here are the various aspects or services of operating system that we will looking for. Let's begin by examining how this operating system handles program execution. The Windows operating system utilizes the portable executable PE format for loading program. This PE format allows for compatibility with a wide range of applications. Additionally, Windows employs virtual memory for flexible memory management, allowing it to efficiently allocate memory to different processes. Multitasking in Windows is achieved through a priority-based system where higher priority processes are given precedence over lower priority ones. Linux system uses the executable linkable format for program execution. ELF is a versatile format that supports various types of executables and shared libraries. Linux employs virtual memory with demanding paging, allowing it to efficiently manage memory resources by only loading data into memory when it is needed. Multitasking in Linux is achieved through fairer scheduling algorithms, ensuring that CPU time is distributed equitably among processes. Mac OS utilizes the Mac object format for program execution. This format is optimized for Apple's hardware and provides efficient loading and execution of programs. Similar to Linux, Mac OS also employs virtual memory with copy on write, allowing multiple processes to share memory resources without duplication. macOS focuses on a responsiveness in multitasking, ensuring that user interaction are smooth and uninterrupted. Next, let's delve into input-output operations, which are essential for interacting with hardware devices and peripherals. In the Windows operating system, device drivers are used to facilitate communication between software and hardware. These drivers operate in kernel mode, allowing them to directly access hardware resources. Windows provides both synchronous and asynchronous I/O models, giving developers flexibility in handling I/O operations. This ensures that application can perform tasks efficiently while waiting for I/O operation to complete. Linux uses kernel also, modules for device interaction, which are loaded into the kernel at runtime. This modular approach allows for better flexibility and scalability in handling different type of hardware. Linux primarily relies on asynchronous I/O for better performance, where I/O operations are performed in the background without blocking the execution of other tasks. Asynchronous I/O improves system responsiveness and efficiency, especially in high throughput environments such as servers. macOS interact with device using I/O kits, which are a set of frameworks provided by Apple for device driver development. These frameworks abstract the hardware details and provide a unified interface for device communication. macOS uses a mixture of synchronous and asynchronous I/O, depending on the specific requirements of the application. This ensures optimal performance and responsiveness while maintaining compatibility with various hardware devices. Now, let's explore file system manipulation, including the types of file systems supported and the mechanism for controlling access to files and directories. Windows. Op- The Windows operating system supports a variety of file systems, including New Technology File System (NFTFs), File Allocation Table (FAT32), and Extended File Allocation Table or XFAT. Each file system has its own set of features and limitations, catering to different use cases. Windows employs access control lists for granular control over file and directory permission. ACLs allow administrators to define fine-grained access policies specifying which user or groups have read, write, or execute permissions on file and directories. Linux offers support for several file systems, with export or Fort Extended File System being the most commonly used. Other files such as X file system and B3 file system are also available, each with its own set of features and performance characteristics. Linux employ user, group, and other permissions for controlling access to file and directories. These permissions are based on the Portable Operating System Interface or the POSIX standard, providing a standardized way of specifying access right. macOS support the Hierarchical File System Plus and Apple File System files. HLFS Plus is the legacy file system used in older version of macOS, while APFS is the modern file system introduced in macOS High Sierra. APFS offer features such as snapshotting, encryption, and improved performance. Similar to Linux, macOS uses a POSIX permissions for controlling access to file and directories, ensuring consistency and interoperability with other POSIX compliant systems. Effective communication between software components and network devices is essential for modern computing. Now let's examine how these operating systems handle network and inter-process communication. The Windows operating system support a wide range of network protocols, including TCP or IP, UDP, and HTTP. Windows provide extensive networking features and APIs for developers to create network-aware applications. For inter-process communication, Windows offer mechanisms such as pipe, shared memory, and socket. This mechanism allow processes to exchange data and synchronize their activities efficiently. Linux is renowned for its robust networking capabilities, supporting a vast array of network protocols and utilities. TCP or IP is the primary network protocol used in Linux, providing reliable communication over IP networks. Linux also offers a rich set of network tools and utilities, such as ipconfig, netstat, and iptables for configuration and monitoring network interfaces and traffic. For IPC, Linux provides mechanisms such as pipes, shared memory, and semaphores. This mechanism enable processes to communicate and coordinate with each other effectively. macOS integrated seamlessly with Apple ecosystem of devices and services, providing a cohesive and user-friendly network experience. TCP IP is the foundation of networking in macOS, enabling communication over the internet and local network. macOS offers built-in support for popular networking protocols, including DHCP, DNS, and Bonjour. For IPC, macOS utilizes mechanisms such as pipes, socket, and MAC ports. These mechanisms facilitate communication between processes and enable the development of robust and efficient applications. Detecting and handling errors effectively is crucial for maintaining system stability and reliability. Let's explore how this operating system approach error detecting and handling. In the Windows operating system, error handling is primarily based on exception handling mechanism. When an error or exceptional condition occurs, such as memory access violation or divide by zero error, Windows generate an exception and transfer control to an exception handler. The exception handler can then take the appropriate action such as logging the error, displaying a diagnostic message, or terminating the offering process. Additionally, Windows provide a variety of system calls and error code for reporting errors and retrieving detailed information about the error condition. Linux employ a different approach to error detection and handling, relying on system calls and error code for error reporting. When a system call encountered an error condition, it returned a negative value indicating the error code. Developers can then use this error code to determine the cause of the error and take appropriate actions. Linux also provides facilities for logging and monitoring errors, allowing administrators to identify and troubleshoot issues proactively. In critical situations, Linux may trigger a kernel panic, halting the system to prevent further damage and facilitating recovery. Similar to Windows, macOS leverage exception for error handling, allowing developers to define exception handlers to catch and handle exceptional conditions. When an error occurs, such as memory allocation, failure, or an invalid operation, macOS generates an exception and transfer control to the appropriate exception handler. Additionally, macOS employ a kernel panics as a last resort mechanism for handling severe errors. A kernel panic occurs when the kernel detects a critical error condition that cannot be safely recovered from, resulting in the system halting and displaying a diagnostic message. Efficient resource allocation is essential for maximizing system performance and ensuring the fair access to resources. Let's examine how this operating system manages memory and process resources. The Windows operating system employs a hierarchical memory management system consisting of multiple levels of memory abstraction, including virtual memory, physical memory, and paging. Windows uses a combination of paging and segmentation techniques to allocate memory dynamically and efficiently manage memory resources. In addition to memory management, Windows also implements process management features such as process priorities and scheduling algorithms to allocate CPU time fairly among competing processes. Linux follows a different approach to resource allocation, utilizing a flat memory model with a single unified address space. This simplifies memory management and allows for a completely fair scheduler or CFS to distribute CPU time equitably among processes, ensuring that no process monopolizes the CPU. Additionally, Linux provides a facilities for controlling resource usage, such as memory limits and CPU affinity settings, allowing administrators to fine-tune system performance. macOS adopt a hybrid memory management approach, combining elements of hierarchical and flat memory models. Like Windows and Linux, macOS utilize virtual memory to provide a unified view of memory resource to processes. macOS employs sophisticated memory management algorithms such as memory compression and memory pressure monitoring to optimize memory usage and ensure responsiveness. Process management in the macOS focuses on prioritizing responsiveness, ensuring that user interaction and foreground tasks are given priority over background tasks. Lastly, protecting user accounts and system security is paramount for safeguarding sensitive information and preventing unauthorized access. Let's explore how this operating system enforces security measures. The Windows operating system provides multi-user access with user accounts, allowing multiple users to share a single system while maintaining separate profiles and permissions. Windows implements security features such as UAC or user account control, which prompt user for permission before allowing certain actions that require administrative privileges. Additionally, Windows relies on third-party antivirus software for protecting against malware and other security threats. Linux supports multi-user access with strong permission control, allowing administrators to define access policies for individual users and groups. Linux employs discretionary access control (DAC) mechanisms such as file permission and access control lists to regulate access to file and directories. Furthermore, Linux benefits from its open source nature, which facilitates rapid identification and patch of security vulnerabilities by the community. These inherent security models make Linux a popular choice for servers and other critical infrastructure. macOS offers a multi-user access with robust security features, including user account with customizable permission and privilege. macOS employs sandboxing to restrict the action of applications and prevent them from accessing sensitive system resources without authorization. Additionally, macOS implements System Integrity Protection (SIP), which safeguard critical system files and directories from modification by unauthorized user or malicious software. These security measures help protect macOS user from malware, phishing attack, and other security threats. In conclusion, each operating system has its own unique features and strengths, catering to different use cases and preferences. Windows offer a broad compatibility and extensive software support, making it a popular choice for general purpose computing and gaming. Linux excel in customization, stability, and security, make it ideal for servers, embedded systems, and developers. macOS provide a seamless and user-friendly experience, tightly integrated with Apple's ecosystem of devices and services, making it a preferable choice for creative professionals and enthusiasts. By understanding the features and capabilities of each operating system, user can make informed decisions when choosing the right platform for their needs. And that concludes for my presentation. Thank you for joining me today for this in-depth exploration of Windows, Linux, and Mac operating system.